All right, we are going to transition to physics. I'll give you more time for the chemistry papers. If you have questions, of course, you know where to find me in my office. I'm usually here until lunchtime every day, at least. On Monday and Tuesday, I'm here later, but after lunch, I usually go home on the other days. But if you need me, you can also reach me in WeChat. You know that. So, all right. So please finish those by next week, so that I can score them and give them back to you, so you have them for study sheets. Okay. 你好，为什么你来这儿？
Pardon?
Why are you late?
So hungry.
Okay. All right. My Chinese is still too bad. I can't ask that in Chinese yet. All right. We are moving on to physics. All right. So we've talked about biology and chemistry. So the next unit in this, or the next section of our chapter on the actual sciences is physics. And again, a reminder, my goal is to teach you the English. I know you are getting this stuff in your domestic classes, and that you get a much broader understanding of them from that. So my goal is to teach you the English, to make sure that when you go to university, you can do your science class and say, oh, I know this stuff, here's how to say it. Okay? All right. So, what is physics? Chemistry is all about atoms and combining matter and changing how matter is combined. Biology is all about life. What is physics?
You study the law of our life.
Not quite. Close.
Particles, movements.
Yeah, the movement. And also, what causes motion?
Force.
Force, or even better, energy. Right? So, physics is the study of motion and energy. Okay? Alright, so, and we have some names for these things, categories. Optics and mechanics. Optics is the study of light, so all those things you all have on your faces are optics. You can thank Brown and Newton for those. They're the ones who figured that stuff out. Mechanics, motion of solids. Okay. Oops, I thought I changed this. Waves, motion of, this should say fluids. Fluid motion, okay. In other words, it's about transfer of energy. So a wave moves energy from one point to another. All right? Energy itself, the forces that do everything. If there's no energy, there's no motion.
Yeah.
There's no physics. Okay? Magnetism. What do you suppose you study there? What do you study with magnetism? What's the root word? Magnet? So you study magnets. And magnets, you study that they are attracted to each other and that they're repulsed from each other. Okay, so attraction, repulsion. Electricity, I know you know what that one is. Electricity sounds like it should be chemistry, doesn't it? It's about the motion of electrons. Okay. And finally we have atomic structure, which gets down into chemistry, so we're crossing that border with chemistry. I'm going to close the window real quick because it's kind of loud. They're butchering the trees. So sad. All right, so the keys to physics. The keys to physics, and pretty much all that we will discuss in our physics unit, are the three laws. Newton's three laws. Okay? So who knows the three laws? Anybody?
What is wrong? I study I'm close to Ahmed. And two interaction forces.
Right? That's the third law?
Yeah.
Okay, can I get you to actually shut that little window tight, please? There we go. There's Okay, well, I'll tell you what, I'll give you a reminder. Here's three laws. Three laws. or a lot of other people who've written fiction about robots have also used these, but we'll come back to those another day. Physical laws. Again, these were written by Newton. Newton stole a lot of his work from a scientist named Brown. Okay, but Newton got all the credit, so we say Newton did this. And the first law is inertia. Does that help? What is inertia? What's inertia?
Friction?
Sorry?
Not friction.
Not friction.
What's the
Inertia? Okay. I-N-E-R-T-I-A.
惯性是吧？是那惯性那个？不是，
Not sure.
不是，
哦
是吗？
the subject just follow the previous motion direction.
Right, exactly. I'm gonna clean up your language a little bit, but you're right on. Okay? So there's two ways to talk about inertia. An object at rest stays at rest unless it's acted upon by an outside force. Okay? And this is what you said, an object in motion will stay in motion unless it's acted upon by an outside force. Okay? So what are some outside forces we can talk about? What's a force that often acts on everything on the planet?
Gravity.
Gravity, right, there's a force pulling. So when we look at this law and say, well, you know, if I roll my ball, it stops. You know, if I had a clear floor for several hundred meters, I could roll the ball and eventually it would stop rolling because gravity is working on it. And there's also the friction of the floor, there's air friction. All these things are acting on it so it slows down. Okay. But if in an ideal situation, like if I was out in space, far away from any planets, and I pushed the ball, it would just keep going forever, or until it hit a star. And it would be sucked into the star by gravity. Okay, so that's inertia. We can also refer to objects. We can say an inertia at rest and an inertia in motion. So you can use it as a noun. We can also talk about it as the action of the object. Okay. So I'm going to make my inertia rest here. Now, according to physics, there's nothing that will ever cause that ball to move until something outside the ball acts on it. It's an inertia at rest until I add force. Then it moves. Falls off the desk. All right. So, when we're dealing with inertia then, we want to calculate it by calculating distance and speed. Speed is a measurement of movement in time in one direction. So when you get in a car and it tells you your speed, what's the typical speed limit in Harbin? 60 kilometers per hour?
Yeah.
Okay, what that's telling you is your car is going that way at 60 kilometers every hour. You could break that down into seconds, meters per second, whatever you want to do. But the car is telling you that you're heading that way. If you turn, now it's telling you you're heading that way. How quickly? Okay? So that's distance over speed. In science, though, we tend to talk about velocity and displacement. Okay? So velocity is also same calculation. Here we have speed equals distance over time. We calculate velocity as change in displacement. So I have delta v over time. Okay, so velocity is generally how fast an object is moving. It can change directions. We're still calculating how fast over how much time. But now we're not so concerned about going in this direction. Anywhere it changes direction, we're still calculating its velocity. Make sense? And then displacement is how far it's traveled. Are you okay? here I have a little line. So if we're measuring an object, there's the start and end of my line. There's supposed to be some start points here. All right, we have a line here going from Xi to Dong. Okay, and if I'm measuring an object, if I'm measuring its speed anywhere on this line, I'm measuring the speed. If it turns around, now I'm measuring the speed the other way. So that's always going to be a positive number. Okay. Well, actually, no. Let me say that again. It'll be positive. If it goes this way, then it'll be negative because now the speed is relative to my start point. Okay. I know it's kind of weird. If I'm measuring velocity, I'm only interested in how quickly it moves over its whole journey. So if it starts at B and moves to A, heading west, I can measure the speed in that. So say it travels at 60 kilometers an hour. Now it turns around and goes back down the same road to C. But it's changed speed. Now there's a traffic jam. So now it's moving at 20 kilometers an hour. My velocity will be the total distance, the total displacement from B to A and A back to C over how long it took it to get there. But my speed changes. The speed from B to A was 60. The speed from A to C was 20. So then I need to cut, if I want the velocity, I have to figure out how far it is from B to A back to C and how much time that took. And then I can calculate its velocity. 明白吗? Nobody's nodding. Is that okay, or is it confusing?
Okay.
Okay, all right. All right, so last year I was not physically present, and I wanted to do a demonstration with my ball. So I made one. Oh, come on, work. Oh, can't do it. Over here. No. There we go. And I have no volume. Okay, so this was me and Siem Reap trying to teach last year's second years. And I'm at the pool at the hotel where we were staying, waiting until we could come back. Then I moved to an apartment in Phnom Penh. But here's my inertia. Okay, and right now you can see the inertia is stable, it's at rest, and again, nothing in the universe is causing that to move. So if there's no force acting on it, it will stay put forever. But I'm about to act on it. Let me see if I can get more sound. It's too bad it's not transmitting through the tube. Nope, that's all I can get. I talk for a long time. Okay, here we go. I'm going to act on the ball. I'm going to act on the ball. Maybe I'll just act on this ball. Okay, ball is stationary. There we go. I act on it. An outside force causes it to move. Now it's changed inertia. Okay? So, and once it's moving, it will keep rolling until outside forces, gravity, the friction of the tiles, they're fairly smooth, so they won't do much, but the transition between tiles slows it down. And that actually drags it a little bit to the right because the tiles aren't laid flat, and it hits the pole by the side of the pool and bounces back. So the inertia is changed again. And then it hits the puddle, and the puddle really slows it down. I'm not quite sure how, but the water, which should be fairly smooth, has a lot of extra friction. Okay. All right, so that's inertia. All right, so let's try it out. We have a chart here, which you can find in your textbooks. Should be about page 91. They changed pages from last year, and I didn't check the page number when I made the spreadsheet. But if you can't see this one, you can look in your spreadsheets on your textbooks.
Here's nothing.
Measurement. Oh. Okay. All right. And you see, we have a chart here. Distance and time. So at time 1 second, its distance is 20 meters. At time 2, 40 meters. At time 3, 60. Time 4, 80. Time 5, 100. Okay, so from that, what can you calculate? Yeah, you can calculate the velocity. So, you found the page number?
Yeah, that's one.
91? Excellent. Good. Okay, so if you have your textbook out, calculate. Figure out the velocity and put it on the chart. And I'm going to turn on the pen so that I can do it. And let's do so it stands up. Okay. All right. Okay. So good. Okay, textbook. Nancy? Alright. See, most of you are getting it, so we'll do it together here. Time 1 is 20 seconds. Time 1, 20. You've done Cartesian planes in math class, right? Time 2, 40. Time 3, 60. Time 4, 80. Time 5, 100. Then I'm going to change colors. We draw our line, connect from time 0, 0 meters. So what can we say about this velocity? It's constant, right? Okay. And it's growing. So it's a constant velocity from time 1 through time 5, time 0 through time 5. And we're moving at what? What is our velocity? 20 meters per second. Okay. That's velocity. Easy enough, right? Let's add some factors. Let's do some calculus. Oops. Alright, I need to erase all my marks now. Clean the screen. Okay, second law. Force. If I apply force to an object, what does it do? I change the inertia. What's its velocity at rest? 0.
But actually, you can't change inertia. It depends on the mass.
Right. But if I apply force, I accelerated the ball, right? Oh, I got your attention. Okay. The ball accelerates. So force causes acceleration. That's law 2. Law 1 is an inertia at rest does what? Stays at rest until acted on by an outside force. An inertia in motion does what? Stays in motion until acted upon by something else. Okay? Alright. So, put my inertia back down. Alright, so force causes acceleration. Alright, so, definition of acceleration. Force applied in the direction of travel or against an inertia at rest. So if the ball's already moving and I apply more force, what happens to the ball?
It will move faster.
It moves faster, right. If I go against the motion of travel, then what does the force do?
What?
If I apply a force against the direction of travel, what happens to the ball?
It will move slower.
It slows down. We call that deceleration. So accelerate, decelerate. D means the opposite But yeah, it means the opposite. So I'm opposite of accelerating. Okay. So we can calculate that in a couple ways. We can calculate acceleration by the change in velocity over time. So it's moving at one velocity, 20 meters per second from our example. And then something acts on it, and now it's moving at 40 meters per second. What's the acceleration? How long did it take to change from 20 to 40? And the total change is 20 meters. So if it was at 20 meters per second at time 1, and 40 meters per second at time 2, the acceleration is 20 meters per second, because it gained 20 meters. So then at time 3, it should be what? Per second, just a second.
Just plus 20.
Sorry?
Plus 20.
Plus 20, so it should be 60 meters per second, but the acceleration would still be 20 meters per second per second. So it gains 20 meters per second every second it's moving with that force. Okay? Back half of the room is not paying attention. Okay. I hope that means you're looking at calculations of force. All right. We can also calculate force by figuring out the mass. Excuse me, we can figure out acceleration by calculating the force and the mass. So our rule is force equals mass times acceleration. So we do a little math and we get acceleration equals force divided by mass. Make sense? All right, simple algebra there. There's one other thing. Again, what force is acting on us all the time?
Gravity.
Gravity. So we can also remember that gravity on Earth at sea level is 9.8 meters per second per second. And you can see how I wrote that. When I have per second, again, simple algebra, I can merge those together and say per second squared. Okay? All right. So, question. If I apply the same force, F, to a large object and a small object, this gets to what you were saying about I can't change its inertia, how will the acceleration of the two objects relate to each other? If I have an object of a small mass and an object of a large mass, say a bowling ball, and I apply the same force to them, what will the acceleration be like? This is the part where everybody goes, oh, he's asking a question, I should look up and listen.
The acceleration will, when the larger object will have less acceleration.
Right, because there's more inertia there for the force to act against, so it resists the acceleration. The lighter object accepts more acceleration because the force has less inertia.
Just as opposed to a ball.
Yeah. All right, so a bowling ball versus a soccer ball. The soccer ball will accelerate much faster than the bowling ball with the same amount of force, right? So, that leads to an interesting question. Why is it that two objects of different masses fall at the same rate? We talked about this earlier in the year. Galileo figured out that if I drop this and a bowling ball of the same size, they'll both hit the floor at the same time. So how can that be what does that mean about the force acting on them?
It's the gravity.
Right. But gravity is the same for everyone, isn't it?
Probably goes to 1 over 2 GT squared.
Right.
That related to mass.
Yeah, so the gravity from the Earth is the same, but we're different masses. And gravity is dependent on the mass of both objects. So, let me check. Gravity equals m1. Is it plus or minus? plus m2, mass 1, mass 2, divided by the distance between them. Right? This should be lower. There we go. So, mass of the soccer ball is smaller than mass of the bowling ball. So there's less force acting on the soccer ball than there is acting on the bowling ball. That's how they follow the same rate. Okay? Alright. Here we have another example video. Yay! Oops. I need to click, not move forward. Alright. So again, I'm going to go through the law. And there I have a pool ball. And when I act on the ball, I add force to it, it accelerates it into motion. So right now its velocity is 0 relative to the Earth. And when I act on it, it accelerates. And then there's other things acting on it, so it decelerates. Blah, 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 blah. I really need to figure out how to get audio from here to here. Look at the screen while I'm talking. There we go. Accelerated the ball. Now what I'm going to do is I'm going to lean down to the big exercise ball, and I'm going to add continual force. And you'll see eventually, for safety reasons on wet pool tiles, I give up because the ball's getting away from me and I shouldn't be running on the pool deck. And it accelerates away from me. So the more I add force, the faster the ball gets. Now here, I'm actually not adding force, even though I'm pushing the ball. I'm pushing with, I gave it a constant force, now I'm just maintaining. I'm adding enough to counter gravity and counter friction due to air. But if I keep adding force to the ball, I'm going to hit the wall really fast. Okay? Every second I'm pushing faster. All right, so force causes acceleration. This chart looks the same, right? Except here, my y-axis, instead of speed, or instead of distance, is now velocity. So now, every second, the velocity increases. Okay? So we calculate that the velocity is meters per second. Okay, again, I know you all know this, but we're dealing with it in English. All right, so what is the velocity of this object? Is the velocity changing?
No.
No. So it's constant. So what's the acceleration?
0.
So acceleration equals 0. Okay. How about this one? Is the velocity constant?
No.
No? Okay. What's the acceleration doing?
It's not negative.
Yeah, it's negative, so we can say it's decelerating. 2 L's. Deceleration. 2 C's, 2 L's. There we go. All right. What's this one doing? We have 0 here.
Decelerates and accelerates.
Yeah, so it decelerates. So here it was moving forward, and it decelerates so much that it stops and moves backward. But these are straight lines still, so this is a constant acceleration, constant deceleration. Okay? It can change. We can lose force. We can gain force. But so here, it goes out, and what would be happening that would cause a ball to decelerate so much that it stops and turns around at a constant rate? What would the ball be doing? What's causing it to decelerate, stop, and turn around?
Friction.
Friction could be one, but friction will just stop it. It won't turn around. So what's a force that could be acting on the ball that would cause it to reach a point where it will stop and suddenly have negative motion?
Direct the other force.
Which force? It's one force. The acceleration is constant, so there's a constant force.
So opposite.
Hmm?
Opposite.
Opposite.
Opposite what?
Opposite of what?
Interaction.
What am I doing?
Something.
I'm accelerating the ball. I push the ball upward. It has a positive velocity. It stops and turns around.
Gravitation. Oh.
Yeah, that's gravity. So gravity is acting at it constantly. And when it falls, here's something cool. At the moment I catch it, it's the same height it was when I released it. It's decelerating. Its velocity is the same as it was here. Or excuse me, as it was when I released it. So it reaches 0 and turns back around. And when I catch it and stop it, the moment before it hits my hands, its acceleration is the same as it was when it was released. And no, excuse me, its velocity is the same. Get my words straight. So, let's look at this velocity of a moving car. Here, my screen. We have 1, 2, 3, 4, 5 segments of this car's journey. So what's the car doing from 0 to 2 seconds? We have 10 meters. This is also in your textbook. It's page 93. So from time 1 to time 2, we go from 0 to 10 meters. What's its velocity? Excuse me. What's its acceleration? It starts at 0. And in 2 seconds, it's at 10 meters per second.
Wait just a second.
Yeah, so it's 5 meters per second per second. All right. Here, from time 2 to time 4, it's moving in a straight line. Okay, so its velocity is 10 meters per second the whole time. What's its acceleration? Acceleration equals 0. All right. Then it moves from 10 to 20 in 1 second. So what's its acceleration? That's easy. 20 meters per second. Actually, excuse me, 10 meters per second, because it's already at 10. Meters per second. Back to 0. And then from time 10 to time 14, it goes from 20 meters per second to 0. So it's 4 seconds, 20 meters change. So 5 meters, negative 5 meters per second. Okay. Getting back on? Alan does. Alan's the one giving me all the answers. Okay. All right, so at what time is the car stationary? When is the car not moving at all?
What?
When is the car stationary?
When in 0 second and in 14 seconds.
Right, here, time 0 and time 14. That's when the velocity is 0. Okay. When is the car moving with a constant velocity?
Between 2 and 4 seconds.
2 and 4, and 5 to 10. It's in your textbook on page 93 if you want to see it better. Okay, next question. When is the car accelerating? 0 to 2 and 4 to 5. Anywhere the line is moving up. When is the car decelerating?
10 to
40.
10 to 14, when the line is moving down. Good. Okay. What is the acceleration of the car? We've already calculated this. The car at time 1, the acceleration is 5 meters per second, or per second squared. Okay. What is the acceleration at time 12? Again, we've already calculated. Negative 5 meters per second. Yo, Tima. Okay. Clean the screen. Ah, no, that's not what I wanted. Come back here. Moving forward. Law 3. All forces are balanced. Or in the language that Newton used, for every action, there is an equal and opposite reaction. This doesn't quite work with humans. If I do something, you can choose to respond. You can choose to respond with a bigger reaction. You can choose to, okay. So it doesn't work with humans, but it does work in physics. So when I act on my ball, well, let's start with 0. What's acting on the ball right now? Same thing we've been talking about the whole time. What force is acting on the ball? Gravity. There's another force acting on the ball.
So 4 and 4.
Yeah, the support force of the notepad. The notebook is keeping the ball from falling, which is why I can rest at 0. So there's an action, a force acting on the ball one direction, and an opposite force acting on the ball in the other direction. Okay? When I hit the ball, that means that the ball is also hitting me. And I can feel it, right? When I hit the ball, I feel the impact on my hand. Okay? And it's the same amount of force. So why don't I go flying backwards like the ball goes flying forwards? When I hit the ball, it goes flying forward. Why don't I go flying backwards?
Because you have more mass.
Yeah, I'm much more massive than the ball. If there's any human, if there's anybody in this room that's not true of, I'm concerned about your health. You should be much more massive than a soccer ball. All right? So, all forces are this way. So again, if I go out into space, far away from any planet or star, there's nothing acting on me, right? So I'm stuck. How do I get out of that spot and get back to a planet so that I can be saved? I need something to act on, right? So I take my super heavy space wrench and I throw the wrench as hard as I can. Now what am I going to do? I pushed on the wrench. I'm going to see if I can get this over everybody's head so I can hit them. I push on the wrench as hard as I can. What's going to happen to me? I'm out in space. The wrench goes flying that way. What happens to me?
No change.
I go that way. Do I go as fast as the wrench?
No.
No. So I have to throw it really hard if I want to get back to Earth. Right? But I can throw my wrench and start moving in the direction I want to go. Then I take part of my spacesuit. Hopefully I don't take a part that lets all the air out. But as long as I have things to throw, I can continue to accelerate by adding force until I reach a point where I'm out of stuff or somebody catches me. Or I run out of oxygen and die. Very sad. Terrible situation. Why do I bring that up? All right.
That's what we got.
So back to me. Now I got wet. Jumped in the pool. All right. So here's me in the pool. And I have an object. Actually, I'm kind of at rest. This pool is constantly drifting. They don't have their jets balanced. But I'm going to act on the water. Of course you saw me. I'm going to act on the water as it moves me forward. Then I act on the side of the pool because I don't want to get all the way out. But once I'm back in the middle, I'm going to act on the tube. And the tube will accelerate away from me. What's going to happen to me?
From the opposite direction.
Yeah, I move in the opposite direction. Not quite as far, but you see I did move a little bit, and the tube went quite a ways. So again, there's me throwing the wrench, getting out into space.